In this lecture, we will learn about the PRIM's algorithm to find minimum spanning tree. So a spanning tree of a given graph GV, E is the set of edges that connects all the nodes of the graph, and it is a tree, which means it doesn't form a cycle. Okay, so for example, this graph ABCD, so these three edges constitutes the minimum spanning tree, because it constitutes the spanning tree because it joins all the four nodes. Okay, so it means that from any two nodes you can travel from any node to any other node in the graph, and this is used quite a lot in road construction, for army, etc. Okay, for postal services also, like you have to connect all the cities. So what happens is that we will now try to learn about PRIM's algorithm. So PRIM's algorithm is basically a greedy algorithm that tries to find the minimum spanning tree of a graph. So what happens is, so we will see a working example which will tell how it forms a minimum spanning tree. So you need, of course, a graph and the weights of the edges, and it also needs the root of the tree from where we want to find the spanning tree. Okay, and finally in the end it will give you a set of edges, and you can find it also gives us a relation pi, where pi of v is u, means that the parent of node v is u. Okay, and key of u is basically, it tells what is the value stored in that node, which helps in finding the minimum spanning tree. So here we maintain a queue. Okay, and that is the min heap queue, which helps us to generate minimum spanning tree. Okay, so let's look with one example, concrete example, which will make it clear. So what happens, I want to find the minimum spanning tree of this graph. Okay, so what this algorithm tells, that first for each of the nodes u which belongs to vertex of graph, we will make key of the vertex as infinity and its parent as null. Okay, so let's try to follow that. So we have so many edges here. Okay, so in fact let's try a much simpler graph. Okay, so we will remove some of the nodes of this graph, and let's say that I just want this graph. Okay, so I want this graph, I want to find the minimum spanning tree. So what we do, so we have all the vertices a, then we have b, c, g, h and I. Okay, so we have 6 vertices, so each of them we have their pi of u and key. Okay, so these are the basic things that they will have. So initially for each of them the parent is null. Okay, so it's nil, no parent is assigned, and then what happens, we have the key as infinity in each one of them. Okay, so this is the case, and then what we do is that we want to start with a root. So we make our root here and its value. So let's start with node A. So we make its key as 0. Okay, and then what it does, and then we include all the nodes in the queue. Okay, so we have all these nodes in the queue. So we have A, B, C, G, H and I, they are in the queue. So now we have this. Next what happens is, let's see. So while queue is not empty, so we extract min. Okay, we do the extract min, which will give us the minimum. So what happens here? Initially we have like this. So extract min, A is the root, it has key 0. So based on that key, it extracts that and we got A. So A comes out, we have A here and we have the key as, so its key was 0. So it got extracted first. And then for each of the V adjacent to U, so what we do now, we try to traverse the graph. So for all the nodes that are adjacent to that A node that is extracted, so we have B and H which are the adjacent to it. So we do what? If V belongs to Q, that means it has not been processed till now, and weight of UV, the edge that is connecting the U to V, if it is less than its present key, then we make the key as edge of the weight of the edge, and parent as U from where it was discovered. So let's again try to see. We have B and C, so it will come, B will come first, and what it will see is that the key of B is initially infinity, and weight of edge UV, U is here is now A and V is B. So weight of edge UV is 4. So it is less than the key. So B will get a key which is now 4. Okay. And its parent will be now A, because from here it was discovered. Okay. So what happens is, then again what happens? We go to H, and H, the key was infinity, now AH is 8, so H also becomes, the key becomes 8 and its parent becomes A. Okay, so now we have these, this is our queue status now. So again what happens? So again this was done, so now we again extract min from the queue. Okay, so we extract the min from the queue. So now min is 4 because B has the minimum key value 4. So B is also extracted from the queue. And then what happens? B, we are at B now. So for each of the adjacent node to B, so we have C and H. So what happens? Again we will see C, the key was infinity, now BC, H is 8. So 8 will be assigned to C and its parent will become B. Okay, and H, so what was happening? H was here, so H is here in the queue and H has a weight now, its key is 8. And now if we come from BH, if it is discovered, so its weight of the BH is 11, and we see from the code that if weight of UV, that is BH, is less than key, which is not the case, so we will not update the key. Okay, so this will not be updated, and hence now what happens? This C has now got a weight key of 8. So now we see again, so we have C has a weight of 8, H has a weight of 8, and then what happens? A and B have already come out. So now we can take out any one of them. So let's take out C randomly because both have equal weight. So we process C out. Now C is there, the main node, discovering node. So for C, what happens? From C we have I and G as neighbors and B also. But what happens? B is now not inside the queue. So if you see the code, so we choose only those neighbors that are inside the queue, which is means they have not been extracted. And then so we see that we will first B we check, but B has already been taken out of the queue. Then it goes to, let's say, I. So I and G. So if it comes to I, then key of I is now infinity, so it becomes now 2, weight of Ci. And what happens, this 2 is the weight and its parent becomes, I's parent becomes C. So I weight is 2, and now it goes to G. So G is now infinity, it becomes 4 and its parent becomes C. So G has got a 4 and I has got 2. So now we have C also has come out. So extract min again, while Q is not empty, we still have GHI. So the Q is not empty, so we will take G, H and I among them. I is the smallest. So we come here, extract I comes here, and from here we again try to traverse all its edges. So C is out of the Q, we will not look at that. H and G, H is there, G is there. So what happens if I discover H from I? So H has a key now 8, and from here it is getting a 7. Okay, so H is now getting a 7 from here. So we will update it and its parent will now become I. Okay, so this happens, and then I also has G. So G has now got a weight of 4, key of 4, and IG is 6, so it will not get updated. Okay, so only thing that got updated was H. Now it became a 7. So now I is done and we have G and H. So G is smaller, so we will take it out. So G, we come to G, and then we see that from G we can go to C, which is already out of the queue. I is out of the queue, and H is there. So H, now key of H is 7, but if we go from G to H, so weight of GH is 1, so it will become 1. So H becomes a 1, its parent becomes G. Okay, so parent is G and H is now the only thing left there, it also comes out, and then everything is processed. So we see, now we will try to make the tree, spanning tree out of this data structure. Okay, so we start from A. Okay, and then what happens, A is the root. Okay, so let's try to make this one. So A is the root, and then what happens, B, let's see B. So B's parent is A, so we go from here, so this is there. Then C's parent is B, so it is like this. Then G's parent is C, so where is G? So G parent is C, and then we have H, whose parent is G. So H's parent is G, and then I's parent is C. So we see that we had how many? 6 nodes. So we have now 1, 2, 3, 4, 5 edges, and this is the minimum spanning tree. Okay, so now let's see what is the weight of this tree. So this is weight of AB plus weight of BC is 8, weight of CG is 6, weight of CI is 2, plus weight of GH is 1. So 8, 4, 12, 12, 6, 18, 21 is the weight of this minimum spanning tree. And you see that we have got the tree. And H, you see that it's initially we estimated its parent to be A, then we updated it to be I, and then finally G. So lot of updates took place because of this part of the code, which was deciding from where we will traverse this. Now let's try to look at the time complexity of this algorithm. So this line, for each u belonging to V of G, So we initialization part, this is the initialization part. It can be done in O of mod V time, because we have V vertices. So we assign key of that, okay, and parent of that to be nil, okay. Then what happens, key of R is 0, which can be done in constant time. Then Q of Vg is Q, we put all the vertices of the graph in the min heap, okay. So this Q is a min heap. So Q is a min heap. So min heap, the data structure to construct the min heap, it will take O of V time. Then what happens, this while loop starts. So this, while this Q is not empty, it has V vertices. So this will run for mod V amount of time, O of V. You extract min, this takes, because the Q is a min heap, it will take log of V, okay. So this is the time complexity for extract min. Then if we see this part of the code, for each V adjacent to U, okay, so this is running over all the nodes, okay, for all the vertices. If we see this part, for loop, okay, so this one, this line, so it runs for how much? So for all the vertices, you are trying to look at all its edges. So there are, it will be summing up for all the di's, and if you sum up all the degrees of the node, that is, we will be looking at all the edges. So if you sum I is equal to 1 to mod V, so this becomes equal to twice the number of edges. It means that we are traversing, we are running this, okay. So this for loop, for each V adjacent to V and these three lines, it is running twice the number of edges times, okay. And then what it is checking, if V belongs to Q, this can be checked, and then if weight UV is less than key V, okay, so these can be done, okay. So this takes O of V log V time, okay. So extract min, let's try to see. So this while loop will run V time, this extract min will take V log V time overall, because we have to do V times this extract min, and then for each V adjacent to V, so this inner loop will run. So this while loop was running, so overall this will run for twice into number of edges times. And again, when we are writing key of V is equal to WUV, so this is again writing into the Q, into some element, the Q. So it will again take O of log of V time, okay. So this takes this much time, so overall this will take O of E into log of V time will be taken by this. So it will be O of V log of V plus E log of V, okay. So now if we see what is the relation, if the graph is connected, then what should happen? So we have the relation that what will happen if the graph is connected. Is there any relation between E and V? So we should have maximum V choose 2, okay, this many. So this should be greater than equal to E. So it means, so E is less than equal to mod V square, O of mod V square. So E log of V, okay, so this will, if you simplify it, so it will come out to be O of E log of V times, okay. So this is the running time complexity with the help of min heap for this PRIM's algorithm, okay. So I hope you understand this lecture. Thanks a lot.